Okay, welcome to lecture 14. During this lecture, we're going to look at two examples of using Green's functions to solve differential equations for Laplace's equation in 2 dimensions. And we sort of two classical examples, but it's very nice to illustrate how you actually construct the Green's function that uses the symmetrical part as one component as well as the additional function that satisfies, make sure that the boundary condition is satisfied. And once again, once you've got this Green's function, it's there for all of posterity. So the examples we're going to look at, in fact, just the one example we're going to look at for the first part of this lecture is determining the Green's function on a disk. Okay, so the technique you go about is pretty much the same as what's been described. It's just different. It's useful to actually go through this yourself and to sort out what the role of the source function and the source point and the field point is, and to sort out over which ones you're integrating when you construct the solution. So there's a lot of, it's straightforward, but you have to be careful with the details when you actually do it. Okay, so the question is, find the Green's function for this equation given basically on a disk D, which is simply everything inside a certain radius in 2 dimensions, and with the Dirichlet boundary conditions. Okay, the one thing I must say is your Green's function typically depends on the equation, it depends on the boundary condition, it also depends, should be obvious, but it isn't. It also depends on the dimensionality of the problem. So the Green's function for Laplace's equation with Dirichlet boundary conditions on a disk and on a sphere are vastly different. Or not vastly different, they are different. And in physics, dimensionality actually plays a very, very interesting role in many places. And this is just another way it gets manifest. For example, charges move differently if they move in 2 dimensions as opposed to in 3 dimensions, right? And an example of a 2-dimensional place where charges move is like in carbon sheets, is an example of a 2-dimensional place where charges move. A normal conductor is 3-dimensional, and their properties is different. You can actually see it experimentally. Okay, and yeah, it gets reflected in the Green's functions as well. Okay, so we want our Dirichlet boundary conditions, which basically is that u is given as a function of x and y on the circle C, and x squared plus y squared is equals to, which is basically x squared plus y squared is equals to a. So just one comment, I'm sticking to, basically stuck to Cartesian coordinates there and then introduced polar coordinates in the sketch. This example is actually done in Philo as well, and I put, for the whole course I went through and I put on lectures that were relevant to the various topics we did, the Philo lectures. I sort of made a list there that have similar problems. So when you're preparing for your test, it might be useful to go and just simply, if you wanted problems to work through, they are at the end of each lecture sort of sampled problems if you would find that useful. So go and look at the course handout. It's not to say you have to know those things in great detail. It's just if you wanted to do more preparation work for the test next week. Okay, so now we do the same thing. We let P be our field point. We let Q over here be our source point. And remember, we're integrating over the source point. We let R1 be the difference between the field point and the source point. Okay, so we have this vector that points from the source point to the field point, and we let R1 just without being bold, the norm of it. So it's basically this length over here, and we do that because we use that to write down our symmetrical solution. So then our Green's function is just the symmetrical solution around the source point, so it's the ln of R1, where that R1 is just the magnitude over 2 pi, plus this potential V1 xy, that's a function of both the source coordinates the field coordinates and the source coordinates. And we're now going to solve for V1, which is what's necessary to construct our Green's function on the disk. Okay, what we have to solve for is that V1 is got to obey Laplace's source-free equation on the disk, and on the boundary C, it's going to be such that V1 is equals to the minus the ln of R1 on the boundary times 2 pi. Sorry, divided by 2 pi. And if we do that, then we've got a valid solution for our Green's equation, and that obeys both the source term or the differential equation and the requirement that G is equals to 0 on the boundary. That's consistent with Dirichlet boundary conditions. Okay, so now we have to find a way of constructing this V so that not only does it obey Laplace's equation, but it also obeys this thing on the boundary. And if you remember, we actually did this problem, this particular one, where you just have the Laplace equation with a source propagated on the boundary. We did it with the Cauchy theorem. Okay, so it's exactly the same problem. This is just another approach to it. Okay, so if you didn't want to go to complex analysis, you could follow this argument. The textbook, I actually think, follows a different one as well. Okay, so there are many ways Green's functions are derived and have been derived in the past. And sometimes you get insight from knowing what the different methods are. Okay, so this picture is exactly the same as that other picture, except that now we only have the source point here on the boundary. Okay, so it's just a different to illustrate the geometry. And the only thing that this basically illustrates is now rho is equals to A. Okay, so here's our boundary. Q is on the boundary. If that is the situation in which we want to specify that V1 is equals to the ln of R1 over 2 pi. And so now if you actually go back and you look at the answer we got that very fancy expression below the denominator, and that comes just from the cosine rule. Okay, so we want to get an expression for what R1 actually is if we want to get V1 to satisfy the ln of it on the boundary condition. And the way we do that is simply the cosine rule applied to that angle. So that's basically theta minus phi, the cos rule, and then we simply have that the one opposite is R1 squared is equals to R squared, which is the distance from O to P, plus rho squared minus 2R rho times cos. So it's exactly just the cosine rule. And you can write down a similar thing for P prime. Okay, so I haven't introduced P prime yet, but for all practical purposes here, it is simply a point on this line extended out of the circle. And if you can remember, we used a similar construction. We were actually solving the analytic problem. In fact, this was probably motivated by that. Okay, there's some of the things in ways of finding Green's functions there isn't a recipe for. Okay, and then you must just find something that works. And this is what makes them hard, and this makes it so useful that once they're found, you can just keep them and apply them several times. So it was a clever person that came out with this argument, but it's not an implausible one. If you start viewing the thing as a source point, here, the reason for picking P1 is simply that you actually want possibly the two impacts of these two sources to cancel each other out in the boundaries. Okay, so that's sort of a rough hand-wavy thing of why people might have thought of that first, but there is actually not a rule. This is one of the, and this is why I actually give you the technique for solving it in two different ways. It's one of the cute tricks. Okay, so for P1, for P prime, we also have this expression where R is just that distance now. Rho remains the same. And here it becomes the trial solution. Suppose, and once again, is I give you the answer and then I show that it works. And that's because somebody did this before and just guessed right and then has given us something useful for the rest of time. So here we have V1 is equals to the ln of something times R2. Okay, so we're constructing the trial solution. Look, the symmetrical solution is the ln of R1. The trial solution, we're adding this thing, the ln of R2, to this other point that lies out of the circle. The reason why this is useful for a trial solution is, one, as long as the point P prime lies outside of the circle, we immediately know that this thing satisfies Laplace's equation. Okay? Because we know that the ln of R1 satisfies, where is it? Satisfies that, okay, for the symmetrical solution of R2. And as long as P prime lies outside, the delta function never spikes, so it actually solves Laplace's equation. So that's the reason for choosing the trial solution. And that's often done, where you basically choose points outside of your domain with a ln. You always have a guaranteed solution to Laplace's equation, and you can arrange it sometimes so that it cancels the other stuff out in the boundary. Okay, so the argument for that would be this thing at least has similar functional form to what this other one has on the boundary. Okay, so now we're simply going to multiply it out, and so there we have, this is just a constant, lambda is just a constant, we have the ln r, and we have that lambda is independent of, well, it's a constant, of q, and phi rho, in other words, the point P, it's independent of q and therefore its coordinates as well. And we have that if rho is equals to a, in other words, q is on the boundary, then we're going to have, we want the case where R1 is equals to lambda R2. Okay, and the reason we want that case is if that is true, we immediately have that V1 is equals to that thing. And so we satisfy the boundary condition. Okay, so if we're on the boundary, this condition holds, and it must hold for all q and rho. Okay, so we have that condition, so we can basically say r squared, which is this r1 squared, which is that thing, must be equals to lambda squared, this thing. Okay, but this expression we want to for it to hold on the whole boundary, so we're going to say it's going to be valid for any angle theta, as well as so this term, the coefficient of the cos term, must vanish separately from the coefficient of the other one. So we're going to have two conditions. The first is that in some sense, this term there's no angular dependence is going to be equals to this guy, and we're going to have that the coefficient of the cos term is also going to vanish. So you're going to have that RA is equals to lambda squared times RA. Okay, so you're basically going to have that R is equals to lambda squared times big R, and then you can substitute this thing back in here, and you get this expression. And you know that lambda is not equals to 1, because you're always choosing R2 to be outside the domain. So we're going to have directly from here that lambda is equals to A of R. Okay, so we've now, off the moment we've had the trial solution, we've now chosen this lambda 2. We know the trial solution obeys Laplace's equation, and then we choose lambda so that on the boundary the trial solution is equals to that thing, and that is valid for the whole boundary, and you're left with this condition. Okay, very, very cute. And once you have it for all time. So now we can simply go ahead and say our full solution is equals to G, which is the ln of R1 over 2 pi plus V1, and V1 is just equals to minus the ln of lambda over 2 pi, where lambda is now A over R, minus the ln of R2 over 2 pi. Okay, so there we have it. Okay, so there's V1, there we just substitute in lambda, and so our final Green's function is just the difference of two ln functions, which we can combine that way. Looks exceedingly simple, but you must remember whenever you want to evaluate this R1 and R2, you actually have to substitute in their expressions in terms of the polar coordinates. Okay, so let's just check. Okay, so once you've got it, always check that it actually obeys what you want it to. You can always, the ln of R1 will always make sure that you have the delta function, the source, in the domain. The ln of R2 never is equals to 0, so it's effectively 0 on the whole domain. And on the boundary, when rho is equals to A, we have this situation where then R1 and R2 we've just substituted in, and that's equals to A over R lambda, which is equals to, and lambda is simply R over A, so it's the ln of 1 over 2 pi, which is equals to 0. And so we have the Green's function that obeys the Dirichlet boundary conditions, and now we can write down any function u in terms of this thing. Okay, so, and also just a sanity check is, if you remember, we wrote down the source-free case. In other words, where G was 0, we wrote it down using the the Cauchy's theorems. Let's just make sure that this thing actually gives you exactly the same answer, because we have the uniqueness theorem, so this term over here must be exactly what we derived using Cauchy's theorem. And so I just want to actually step by step go through getting from this expression in terms of the R's to actually evaluating it in terms of coordinates. Okay, so let's now write out the full integral. So u of r and theta is simply the integral from 0 to a, so it's over the circle, the integral over the radius, times 0 to 2 pi, times 1 over 2 pi, our Green's function, times g, times the full area element, which is rho d phi times d rho. Okay, so this integral has now been put in spherical coordinates, so you're having the Jacobian, the normal Jacobian coming in there, and plus the integral from 0 to 2 pi, because you're integrating over the circle's boundary, times u times dg dn times the line element, which is a times d phi. Okay. So in the g equals to 0 case, you're only interested in this last term where f of theta is given on the boundary, or sorry, if u is equals to f of theta is given on the boundary C. And so we have basically this situation again, and you have this thing that u of r and theta is equals to from 0 to 2 pi f of theta dg d rho times a d phi. And now all I'm going to do is check that dg d rho is equals to what we actually anticipate from the Cauchy theorem. And to do that, we basically need to compute where's g now? What the derivative of this thing does with respect to rho. Okay, so the nice thing is R doesn't contain rho, A doesn't contain rho, it's a constant, but rho does appear in R1 and R2, okay, because it basically scales where on earth the source point is. Okay, so let's see how we actually just compute it without getting ourselves completely stuck in algebra. I mean, in principle, what you could have done is you could have substituted in what the expressions for R1 and R2 directly in here and taken the respect to rho. And this is just a trick that you can do it implicitly. Okay, so let's just write it out. So it's simply a chain rule over there. And we expand this guy, so we want to compute these guys. And the thing that I'm going to do is simply try and get the R1 squared and the R2 squared over there, because that's what we have easy expressions for. Okay, so I'm going to basically multiply this denominator in there, so I have 1 over R1 dR2 over d rho, but that's exactly equals to a half times partial R1 squared d rho times 1 over R1 squared. And then you have this exactly the second term. And these things are now easy because we know what R1 is in terms of rho, R1 squared is in terms of rho, and R2 squared is in terms of rho. And there they are. Okay, so dr1 d rho is just that. dr2 is just also from the cosine rule, so it's just dr2 d rho is just that example. And therefore, on the boundary, where you have to evaluate the integral, you basically have that rho is equals to a, so that's another thing that we can substitute in there. But be very careful, you can't do that before you've actually taken the derivatives. Okay, so you could do that for all the other things that entered the R1, the R2 that enter in the denominator, but you cannot substitute it in before you've taken the derivatives over here. And you can also know that on the boundary R is simply equals to a squared over R, which is due to the lambda that we derived. And R2 is equals to a over R1. And so you can evaluate dg d rho at rho equals to a equals to this thing. And now you're simply going to put in what these expressions actually are and set rho equals to a. So there they are. And what you then get is this expression, and then you're left with 1 over R1 squared, which is that term. And you're left with exactly the same thing as you derived from the Cauchy's theorem. Okay, so the Green's function constructed that way actually hides a lot of complexity, right? Because the R1 and the R2 that actually gives you a very nice geometric picture of how to construct the function on the boundary is actually quite complicated to work with when you start taking derivatives with respect to rho. But it can still be systematically done. Okay, so people tend to work with what they find more comfortable. Okay, if I'm working in 2 dimensions, I like Cauchy's. My feelings for the complex plane is easier, then I do it that way. When you go to higher dimensions, Cauchy's thing no longer exists. Okay, so then you have to work with a full Green's function that also actually depends on like the norms of vectors between the source function and the point where you actually, the field point, and some other points that you put outside to actually try and cancel out the boundary terms. So the things that you see, or the characteristics that you see in this example, tend to generalize, but they do hide complexity that you actually have to go through carefully to try and understand. Okay, so we're now left with the final answer, where u of r and theta is just the integral from 0 to 2 pi f of phi times dg d rho times a d phi, where dg d rho is equals to this little beast. And the a cancels that a, And there we are, which is exactly the same solution as you got from the Cauchy's theorems. Okay. So I think that's the end of the circular disc example. Go through it on your own. It's actually very pretty once you start understanding the geometry. This is a simple example of something that people call this choosing the points outside, that in some sense cancel out the Green's function below, or the other one on the boundary. It's a method they call the method of images, okay, where you actually view. So another example would be, suppose you wanted to find a Green's function that has the potential that's equals to 0 on a flat plane. So one way of constructing that would be to take your symmetrical Green's function of one charge and then to put another charge exactly below the plane. So once again, you're going to have it satisfying Laplace's equation above with no source, and you're going to have that the potential exactly on the surface between the two is exactly 0, and that allows you to satisfy that boundary condition. So in some sense, you have this idea of image charges that behave the same, that cancel out the effect of the actual Green's function, the source-free Green's, the symmetric Green's function on your specific surface that you're interested in. And a lot of the solutions were actually constructed that way. There are other techniques, and we'll look at that tomorrow. So tomorrow is actually going to be quite a short lecture then, when we just look at the rectangular domain. But it's another example that illustrates sort of other things as well. It starts illustrating the Fourier series. So we'll do that tomorrow, and then that's done, and then the next time I see you is for the test on Wednesday. Cool. And then I can actually go to the meeting. They suddenly jumped on me as well.